So in this video, we're going to look at how order finding can help us factor an integer. So recall that the order finding problem computes the order of an integer x. So it computes x to the r, or it finds r such that x to the r is congruent to 1 mod n. Right? So x is the given integer, and we have to find the order of x. Now, to go from order finding to factoring, we've used the following theorem from number theory. So the theorem states the following theorem. So if n is odd and not a power of prime, then there is a probability of greater than half that r is even and x to the r over 2 plus 1 and x to the r over 2 minus 1 are not multiples of n. So this is a theorem in number theory that we'll be using. Let's see how we can use this theorem to find the factor of n. We have to use this theorem and the fact that we have an efficient algorithm to find the order of x. So if r is the order of x, then x to the r is congruent to 1 mod n, right? I can get 1 to the other side, use the properties of congruency. So this is x to the r minus 1. So I can write x to the r as x to the r over 2 square minus 1 is congruent to 0 mod n. So this is x to the r over 2 minus 1 into x to the r over 2 plus 1 is congruent to 0 mod n. Now suppose x to the r over 2 minus 1 and x to the r over 2 plus 1 are not multiples of n, but their product is a multiple of n, right? So over here, the product is a multiple. So this implies that x to the r over 2 minus 1 into x to the r over 2 plus 1 is equal to some k times n. If either of them are not multiples of n, then we must have that each of them share a factor with n, right? So if both x to the r over 2 minus 1 and x to the r over 2 plus 1 are not multiples of n, then both of them must have a common factor with n. So then both must have a common factor. And we can produce these common factors by computing the GCD of x to the r over 2 minus 1 and GCD of x to the r over 2 plus 1. Okay. So the algorithm that we are going to show to produce the factor is the following. So we are going to use this theorem from number theory. So what we'll do is that we'll randomly choose an x which is less than capital N, and then compute the order of x by sending x to a quantum computing subroutine. Once R is computed, we will check if R is even and whether these two other properties, x to the R over 2 plus 1 and x to the R over 2 minus 1, are not multiples. In fact, what we have to do is just check that x to the R over 2 is not congruent to minus 1 mod n. So that's the check that we have to do. And we are guaranteed that R is even, and this happens with probability greater than half, right? And then if this check passes, then we can compute the GCD of uh, x to the R over 2 minus 1 and GCD of x to the R over 2. They are guaranteed to be factors of n. So let me just write the algorithm. So algorithm is the following. Algorithm to find a factor of n given an order finding quantum subroutine. Right. So first is randomly choose an x less than n. Okay. Well, if GCD of x comma n is greater than 1, then this itself, GCD x comma n itself is a factor, and return this as a factor. If GCD x comma 1 is equal to 1, then call the order finding subroutine of x, and I should get back an order. This should be a quantum subroutine. So this is a quantum routine over here. All right. And then once we get back R, we have to check if R is even and x to the R over 2 is not congruent to minus 1 mod n. That means that x to the R over 2 plus 1 is not a multiple of we don't have to check x to the R over 2 is not congruent to 1 mod n, because R is the order. So it is the smallest integer that x has to be raised to get to 1. So this we don't have to check. Right? So check this fact. If it is true, then return a GCD of x to the R over 2 plus 1 comma n, or GCD of x to the R over 2 minus 1 comma n as a factor. If not, then you can go back. Well, if this fails, right? If r is not even, or x to the r over 2 is congruent to minus 1 mod n, then else return to step 1. Right? So that's how we convert the order finding routine, subroutine to factoring routine. And the only quantum step over here is the order finding subroutine, and which we have shown that is efficiently done by the quantum computer.